Okay, so our focus, I know it says I can write and graph step and absolute value functions. We're mainly focusing on the graphing aspect of step and absolute value functions. So we're starting out with step functions. So if you just take a look at this graph here, you can probably see why they're called a step function because the graph looks like steps, it looks like stairs. They are not connected here though. So I know when I say they look like stairs, they're not connected like by vertical pieces here. But it says at the top, so how these are similar yet different than what we did on Friday. So Friday we were focusing on piecewise defined functions. All of our pieces were linear, but they wouldn't have had to be. When you saw the expression or the function itself, you saw multiple pieces to it. Here we are just focused on piecewise linear functions, and these contain a single expression. So when you see the function given to you, you're not going to see that it consists of multiple pieces. You just have to know when you see the function that it would be a step function or that it would be absolute value and then what that would look like. The step function that we are looking at is, well, it says a common piecewise linear function is the step function, and it consists of line segments, so it looks like steps. But the step function we are focusing on is called the greatest integer function. And it's written this way. So f of x equals, and so it has like a double bracket with your variable x somewhere inside of there. And that symbol means the greatest integer that is less than or equal to x. So very wordy for one symbol, but if you're looking at this, you're saying f of x is equal to the greatest integer less than or equal to x. So what that means is, first of all of your output values from this are integers. So if I have 3.25 in here, I'm figuring out what is the greatest integer that is less than or equal to this number. So the easiest way I can describe it is to think of when you have a number inside of those double brackets, think of the two integers that it's in between. Like 3.25 is in between 3 and 4. So the greatest integer that is less than or equal to that would be the smaller one, the 3. So this, as an operation, would equal the number 3. If I substitute 3.25 into there, my output value is 3. Another way to think of it is you're always rounding down. No matter what number is in here, you're always rounding down. So if I have negative 4.6, using that same logic, what would that be equal to? Or rather, what two integers is it in between? Negative 4 and negative 5. So what would this equal? Which one is smaller, negative 4 or negative 5? Negative 5 is smaller. So on a number line, because you'd have negative 5 and then negative 4, so you're always rounding down. So rounding down would round to the negative 5. And then if you have an integer in there, then, because it says greatest integer less than or equal to x, so then it's equal to itself. So if you're inputting an integer, your output is that same integer. So even if, like if I were to put another one up here, even if I had like 0.999, okay, that is going to round down. The output for this is 0. Okay, because that is between 0 and 1, and so it would round down to the 0. So that's what that symbol means. Then this is what the graph of just the greatest integer less than or equal to x looks like. And when we actually go through graphing this, I'll explain why it looks that way, but it looks like steps. Notice in each little line segment, one endpoint is a dot, one endpoint is a circle. Again, so it remains a function and passes the vertical line test. The domain for this, x can be any real number. So x such that x is an element of the real numbers. And then the range, All of the output values just for the greatest integer less than or equal to x are integers. It's all of the integers. So notice like y could be 0 or 1 or 2 or 3 or -1, -2. So it's all of the integers. So I'm going to write here underneath all integers, but I'm going to show you how to write that using the set builder notation. So it'd be all values y such that y is an element of. Anyone remember the letter that symbolizes the integers from chapter 1? Z. So I kind of make a Z with this kind of being doubled up. So y would be an element of the set of all integers is what that would mean, where r is the set of all real numbers, z is the set of all integers. Okay, so we're going to go through an example. Yeah, band people, if you have to leave, you can grab an assignment up here. Like I said, this will be on Canvas. But we're going to graph f of x equals -2 times the greatest integer less than or equal to x minus 5, and then identify the domain and the range. What you want to think of or kind of put into your mind is that anytime you see those double brackets in a function, to just know that that is going to be a step function when you graph it. Just to make that connection, whenever I see these double brackets, my graph should look like this. That way, because I'm not going to be telling you in the directions, that this is the graph of a step function, so just to be able to recognize that. But I graph these by making a table. So I'm going to set up an XY table. And the values that I'm going to substitute in for x, I substitute in a mix of some are integers, some are decimals. And I usually pick the same ones every time, but you wouldn't have to. So I usually start with 0, and then I do 0.25, 0.5. I kind of skip 0.75, and I just jump to 1 and do 1.25, 1.5, and then 2. And you could keep going. I tend to stop there because what you're going to be looking for is a pattern in the y values. And once you find the pattern, then you can go ahead and graph it. And you'll see what I mean there. So if I start with 0, inputting 0 into here, so I'll have -2, and then greatest integer less than or equal to 0 minus 5. And I have to calculate this. So those double brackets are a grouping symbol. Evaluate inside of that first. So 0 minus 5 is -5. And so this is where what I was going through up here, you figure out what this value would be and then multiply it by -2. So because -5 is an integer, it would just stay -5. So this is really -2 times -5. So that'll be 10. So this y value is 10. Okay, so then if I substitute in 0.25, .25 minus 5 would be -4.75. So again, I need to calculate what this value is before I multiply by -2. So the -4.75 greatest integer less than or equal to that, what would this become? It would become -5. So this is still -2 times -5. So the y value is still 10. Then if I plug in 0.5, I would do 0.5 minus 5 is -4.5. Greatest integer less than or equal to -4.5. So what does this become? -5 again, so I still have -2 times -5. So this is still 10. Then if I plug in 1, So 1 minus 5. 1 minus 5 is negative 4. But now negative 4 is an integer, so this is just going to stay negative 4. So this is negative 2 times negative 4, so that'll be 8. So now if I plug in 1.25, what do you think the y value is going to be? Not 10. It'll be 8. 1.5. What do you think the y value would be? 8. What do you think the y value will be when I plug in 2? I heard some whispers. It will be 6. So notice, starting at 0, once I got to the next integer for x is when my y value changed and the y value had gone down by 2. So then when I get to the next integer for x, the y value will go down by 2. So 2.25, the y value would still be 6. So it's not even like you need to plug in every single number you choose in your table. Plug in enough x values for you to notice what the pattern of your y values is. Then, to go over here to start making the graph, these are all points on your graph. So I'm going to start with the 0, 10. So I would plot 0, 10 with a dot. And then I could plot 0.25, 10, 0.5, 10. So 0.25, 10 would be about here. 0.5, 10 would be here. I didn't plug in all of the decimals that are between 0 and 1, but any decimal all the way up to 1, that y value is going to stay 10. That's where the horizontal line segment comes in. But when I actually got to the x value 1, the y value is no longer 10, it jumps down to 8. So that's where I have a line segment that goes over to 1, 10, but I have a circle there because when x is 1, I need to jump down to start my next step at the y value 8. And that's where my next dot is. And then I continue that pattern. So that line segment will go over to when x is 2, and I'd have a circle because at 2, the y value, the next step has to start down at 6. Okay, and then you just keep drawing those steps. So at 3, the y value is going to jump down to 4. At 4, it jumps down to 2. And you keep drawing as many steps as you can on your coordinate plane. So if I could also go the other way, the other direction, I would. It's just based on where we started. I can't like continue this up like that. But I did include all of the steps that would have fit on that coordinate plane. Okay, so questions there on the graphing part of it. They're a little weird, they're a little different. Okay. Domain, so for the step functions here, the domain is always going to be all real numbers because you can plug any number you want to in for x. So x such that x is an element of the real numbers. The range, though, is not like the range up here is all integers. This range is not all integers because if you look at our y values, we have the y values 10, 8, 6. We don't have the y value 9, the y value 7, the y value 5. So how would you classify what y values we do have? Well, they don't have to be positive either because we do have like this y value of -2, -4, -6. They're all what? They're all even. So these y values are all of the even integers. So there's not really a nice way to write that in set builder notation. So this I'm just going to write into words. I'm going to say the range is all even integers. Or you could say another way to phrase that would be integer multiples of 2. Because you might have a graph where maybe your y values are like 3, 6, 9, 12. So they don't fit into that category of they're all odd or they're all even, but they go by threes, and you could say integer multiples of 3. So this would be 2 different ways to say the same thing. But unless you have something else in your expression here that gives you a decimal for the y value, your range is going to be some variation multiples of integers. But as I guess, like I said, it doesn't have to be if there's something in here that would get you a decimal. Like if then I was doing 10, but on the outside of this I had to subtract 0.5, so I got 9.5, something like that. But you're looking at how to classify that. So questions there? Okay. Let me see here. I want to leave you some time to work. I'm going to skip example 2 for right now, so that we can get on to absolute value, and that way you have some time to practice this, or more time than you would have if we went through that. We can always come back to it another time. But I have on the back, so now getting into absolute value. So another type of piecewise linear function is the absolute value function. Absolute value function you can recognize, it's a function that contains the algebraic expression within absolute value symbols. So if you see absolute value symbols, know that you have an absolute value function. The f of x equals absolute value of x, that is the parent function, so that is the simplest absolute value function, and make note that these graphs should be in the shape of a V. So all absolute value functions should have a V for their graph. This shows you why it's piecewise, so we will not write it this way, but this shows you why it's piecewise. It's composed of 3 pieces. If the x values are positive, so that would be the right side of your graph, this side, it is made up of the line y equals x, so a slope of positive 1. If the x value is 0, the y value is 0, so that's the point 0, 0. This is called the vertex, so similar to parabolas, they have a vertex. And then if the x values are negative, that's the left side of your graph, then this is the line y equals negative x, so the slope is negative 1. So it is composed of 3 pieces, but you'll always see it given like this. I'm just going to label this here too, that this is called a vertex for an absolute value graph. And then it gives other information about the parent graph, the domain, the range. Domain for these, again, is always going to be all real numbers, no matter what. The range will change, and it gives the intercepts as well. But we'll look at example 3. So it says graph f of x equals the absolute value of 2x minus 4. Identify domain and range. So when I see, again, I have absolute value bars, I know my graph is going to be a V. It could be a V that does open downward as well. What I typically do, I still make a table to graph these, but the first thing I find is where that vertex is going to be, the x value where the vertex will occur, so that I know what values to plug into my table. And to find the vertex, you want to take only what is in the absolute value bars. So in this case, the 2x, I don't include the minus 4. So I just take the 2x and I set it equal to 0. So to find the vertex, you take what's in the absolute value bar, set it equal to 0, and then you would solve it for x. So in this case, if I solve for x, divide by 2, I get x is 0 divided by 2 is 0. So this is the x value of my vertex. So in my table, I'm going to stick the x value 0 towards the middle, because that's where my vertex is. And then I want to substitute in values that are on either side of that. So I'll just do like 1, 2, and then -1, -2. So a couple values on either side. But it'll not always be, the vertex is not always at 0. It might be a lot of the time, but it doesn't have to be at 0. So it's not that these are always the values to plug in. And then I can just substitute these into my function. Careful that you're actually taking the absolute value though. So for example, if I plug in -2, I have the absolute value of 2 times -2, and then -4 on the outside. 2 times -2 I know is -4. So I have the absolute value of -4 and then -4. What is the absolute value of -4? +4. So this is 4 minus 4, so that y value is 0. Okay, so I see a lot of the time if you do not actually take the absolute value, you will not end up with a v. You'll end up with just a straight line. And that's just your clue thinking about the function that it should be a v, that something isn't right. So now if I plug in -1, I'm not going to write all of these out, but 2 times -1 is -2. The absolute value is +2, and then 2 minus 4, this would be -2 for the y value. And if I plug in 0, 2 times 0 is 0, the absolute value is still 0, -4 is -4. Then if I plug in 1, 2 times 1 is 2, absolute value is still 2, -4 is -2. And plug in 2, 2 times 2 is 4, absolute value is still 4, -4 is 0. So notice, just like if you remember, because I know we haven't graphed, well, we graphed 1 in 2.1, but we haven't spent time graphing parabolas yet. But parabolas have this same symmetry property where you have a vertex, and then on either side of your vertex, you have the same y values. That'll happen, and that should happen to make your v. So now if I plot these, you should see that it creates a v. You can draw the v in. Okay, the domain, like I said, for these is always all real numbers. X can be anything. So X such that X is an element of the real numbers. The range, though, will never be all real numbers for these, or it shouldn't be. Anyone know how you'd classify the range for this? So all y values such that, what would you say for the range for y? Yes, y is greater than or equal to -4. So you have if you bring it to the y-axis, your lowest y value is at -4 and the graph is extending upward. So all y values that are greater than or equal to -4. Okay, questions there? Okay, and I know there's another example. Like I said, you could have a v that does open downward, but I want to pass out the assignment so you have a little bit of time to work as well.